Hi students, welcome. It's Dr. Maya Dunne. I'm explaining in this video about the energy changes and chemical reactions. This is the thermodynamic chapter. So this is the topics that we are covering in this lecture. We talk about energy and energy changes, introduction to thermodynamics, enthalpy, and I'm going to touch base a little bit with calorimetry, standard enthalpy of formation, and then we're going to go with the bond enthalpy of the some reactions, covalent bonding. So let's see what is the energy and the system. So the system is the part of the universe that is a specific interest. If you think about a water bottle, just the water and the bottle itself is a system. Everything else is a surrounding. So basically the system is the part that we are interested in studying the energy changes. And the surrounding is everything else other than the system. So in this diagram, you can see the red color is the system, everything else is the surrounding. Universe is the big part which is made out of system and the surrounding both. The system is usually defined as the substances involved in the chemical and the physical changes. So, thermochemistry is the study of heat, heat transfers, basically the study of heat transfer. Heat is the transfer of thermal energy. How heat transfer from the system always, when we study the heat transfers, the heat transfer is the system. Think about you have the closed water bottle. We study the heat transfer from system to surrounding or from surrounding to system. So SI unit is joule, heat, often used in calories. And so this is so 1 calorie is 4.814 joules. I don't want to memorize the conversion, but you just need to always joules are higher than the calories. But it's if you think about the calories in the food calorie, it is 1 calorie. Like you see the uppercase CAL, it's like 1,000 smaller calories. So it's calorie is not the same as the nutritional calories. It's different. So energy changes can be mainly two ways: exothermic, endothermic. What is the exothermic? Exothermic is when system release its heat to the surrounding. Here you see this is system, it releases heat to the surrounding. So when you think about the water bottle releases heat to the surrounding. When you touch the water bottle, you feel hot because the system release heat, the energy, the heat, then you can feel the heat. And then endothermic, system absorbs heat from the surrounding. So when the system release heat or system release energy, the system energy decreases, right? So and then when the system absorbs heat in endothermic reaction, system energy increases. So that is the important things you need to know. What is the exothermic process? What is the endothermic? Always exothermic system release heat. The heat is decreased, and the endothermic absorb heat. And then thermodynamic is the study of interconversion of heat and other kinds of energies. When we study thermodynamics, we'll study open system, closed system, and isolated system. You can see this is an open system, water in a cup, always free to exchange the heat with the surrounding. Closed system, so the cup is closed. This is a round bottom flask, but in the closed system, still you can transfer heat. Isolated system, it does not exchange heat at all. Okay, so the states and state function. So the state functions are properties that are determined by the state of a system, regardless how the condition was achieved. So you need to know what are the state functions, what are the non-state functions. So basically, energy. Energy, you always consider how much energy at the beginning, how much energy at the end. It doesn't matter what happened in between. Pressure, how much pressure at the beginning, at the end, volume, temperature. So these are some state functions. With this, I'm going to first, with keeping this all in your mind, I'm going to go to the first law of thermodynamics. First law of thermodynamics states that energy can be converted from one form to another, but cannot be created nor destroyed. So energy cannot be created or destroyed. So this is the first law of thermodynamics. U is the change in internal energy, just the signs and the names, and just the energy. I mean, energy by itself, like energy. So it's the delta is a change. This delta sign is always be used for the change. U is internal energy. Just think about it's energy, but it's another letter. So the change in the system, change of energy in the system plus change of the energy in the surrounding equal 0. Why? Because whatever the change, like if the system release heat, surrounding supposed to absorb that. So there shouldn't be any change. So that's what I say delta U system plus delta U surrounding equals 0. So delta U equals U final, U initial. Always delta U system equals negative delta U surrounding. What does that mean? So system release heat. So system absorb heat. How system absorb heat? The surrounding releases that heat. System absorb heat from the surrounding. Okay. And then we learn another thing, another word, which is work and heat. The overall change in the system's internal energy. So the system, now we talk about the system. I want you to think about, okay, we're talking about a water bottle. It's a closed water bottle. And then that's our system. So the delta U, internal energy of the system, equals Q plus W. What is Q? Q is heat. It's a positive for endothermic process, negative for exothermic process. Positive for endothermic process means heat absorbed by the system. Q negative is heat released by the system. W is work. Work is positive when the work is done on the system. W is negative, work done by the system. System has to do work. When you have to do work, you get tired because you lose energy. Something like that. Okay, so this science and this, you need to know each letter denotes what? U, internal energy. Q, heat. W, work. And also what is the sign says? Q can be positive or negative. Q positive means heat absorbed by the system. When the system absorbs heat, it is endothermic because then more heat in the system. Q negative, heat released by the system, exothermic. So work done on the system, W positive, work done by the system. The system has to do work at that time, W is negative. So I have a question. My question is, calculate the overall change in internal energy delta U for a system that absorbing means exothermic or endothermic. Endothermic, right? Because when your system absorb heat, it's positive and does the work. So system has to do work. That means it's negative. So that's what I wrote. Okay, the internal energy of the system equals Q plus W, 1.88 positive plus negative 141. It's 47 joules. Enthalpy, reactions carried out at constant volume or at constant. So now we've talked about internal energy and we talk about Q and W. And now I'm going to we are still in the first law of thermodynamics, but I want you to introduce another term. This new term is enthalpy. What is enthalpy? Enthalpy, the reactions carried out at constant volume or at constant pressure. So we call that the energy release called enthalpy. So this is a reaction. Sodium azide denotes to give large quantity of nitrogen gas. So it's sodium azide, sodium and nitrogen. Under constant volume conditions, pressure increase. If you do under constant pressure, volume increase. So there's a relationship, right? The pressure volume. PV work is done when there is a volume volume change under constant pressure. So when there was a work is the pressure. So the work W, you can write P delta V. Work is W P negative P delta V. What is delta V? Delta means V final, always delta final volume minus initial volume. Now, I want you to tell something. Think about this one. So here the final, think about, okay, this is the final volume is 100. Initial volume is 50. So final minus initial. So the gas is expands, right? Gas expands. So always, you see here, I'll show you here. Delta final minus initial. Like that, here also, final minus initial. So final, so now the system has to do work, right, to expand. So the final is 100, initial is 50. Think about it, it's like at the beginning it's 50 milliliters, at the end it's 100 milliliters. So 100 minus 50, it's 50. Pressure, think about that happens in the atmospheric pressure, which is 1 always. Sorry. So negative P delta V. So that gives you, okay, W is negative. Why? In order to expand, system has to do work. Think about the other way. Initially, you have 100 milliliters. Somebody push it down. So now final volume is 50. Now final is 50. Initial is 100. 50 minus 100, negative 50. Negative 50 and pressure is 1, atmospheric pressure 1. Negative 50 multiplied by 1 and it's negative, so it's become positive. When the volume decrease, it's somebody has to done work on the system, so then work is positive. Now I have a question. Let's look at the question. Determine the work done in joules when the sample of gas extend from 552 milliliters to 891 at a constant temperature against a constant pressure of 1.25 atm against constant pressure of 1 atm against vacuum. So let's look at the delta V. So then they ask us to do the work. So the work is W is negative P delta V. So the always the negative P delta V. So my question is, okay, so the delta V we know 891 final 552. So now I know the delta V is 339. A pressure is 1.25 atm. So I have the 1.25 atm multiplied by 339. But you can't do that because they ask you, there's a unit conversion. What is the unit conversion? You need to convert work done in joules, but I have here in atm. So one liter atm is this much joules. So I want to first convert milliliters to liters. That's what I did. 1 liter equals 1000 milliliters. And also the conversion of ATM to joules is 1 ATM is this much joules. Now I have 1.25. So 1 liter you multiply by this number. So then I get work 42.9. I know that you can easily find the pressure and the volume, but the unit conversion is the one little challenging because you want to convert this milliliters to liters, which is why you multiply by 1000, divide by 1000, and then 1.25 atm, 1.25 atm convert to the pressure, in so because you want to give the final answer in joules, atm, how to convert to joules. So 1 liter atm is 101.3. So that's why you just multiply by this number. Like that, you did this question. So you always just get the change and then change the pressure and then convert to volume to liters and then liters atm. So that's how you do this question. And then I have the other part, which is the so previously we talk about the reactions that carry out at the different pressures, the changing volume. Now the reactions carried out at constant volume or at constant pressure. So the pressure volume or PV work is done when there's a volume change under constant pressure. So, but if you think about this equation, delta U, internal energy of the system is Q plus W. Now we know W is Q plus negative P delta V. When a change occurs at the constant volume, delta V equals, so when there's a constant volume, there's a no volume change, so then no work is done. When there's no volume change, no work is done, so always internal energy equal to heat. So the reactions carried out constant volume or at constant pressure under conditions when there is a constant pressure, Q plus W, Q negative P delta V. So this is just rearranging the equation. Heat equals internal energy. So just take the negative P delta V to this side. That's just rearranging the equation. Now I told you about enthalpy. What is enthalpy? Let's go back to the enthalpy. Enthalpy is okay. Enthalpy is the enthalpy. Okay. Actually, enthalpy is the heat. It's basically we said okay, it's the heat heat carried out by constant pressure or constant volume. So if you go here, you see internal energy equals Q plus W. So you subtract the W by negative P delta V. And then I come here for the enthalpy. The thermodynamic function of a system is called enthalpy H, is given by internal energy and pressure volume work. So you can always, whenever you have this equation, make sure you have everything in the same unit so you can add it. So then this is some rearrangement going, but it says, okay, delta H is delta U, change in the internal energy, change in the pressure volume work, and then delta H equals delta U. You take the constant pressure, P delta V, delta U, delta H, P delta V, and U, so then delta H is enthalpy or heat. So you take, this is instead of this delta H, you write Q, and then you take the P delta V to this side, and then you have delta U plus P delta V, and then substitute equation 3 into equation 4 and you solve. At the end, I know there's so many things going on, but I just want to know theoretically, you just want to know enthalpy is heat. I'm not going to ask in the exam, show this. No, I'm going to ask the theory, the knowledge, the fundamentals. So you just need to know, okay, enthalpy is heat. So that's about the main theoretical part of enthalpy. If you know the heat of a reaction, heat of an element, that is the same as enthalpy. Enthalpy of a reaction, if I ask you, okay, find the enthalpy of the reaction. Enthalpy of a reaction is difference between enthalpy of the products and reactants. So that's what I shown here. Delta H is its products and its reactants. Always it's a similar rule apply. Delta H bigger, positive, that is endothermic. Delta H smaller, negative is exothermic reaction. So, in the thermochemical equations, thermochemical equation is important when you have the thermochemical equations, the sign of the delta H. Positive, endothermic, negative, endothermic. And also, what is the system, what is the surrounding, those things you need to know. So, if you take this equation, this is the water solid becoming water liquid, but is melting, right? So, it's positive, it's endothermic reactions. This is methane gas, it's combustion, methane gas combining with oxygen. So this is releasing heat, this is the exothermic reaction. Thermochemical equations, you need to know that is enthalpy is an extensive property. Extensive properties are depend on the amount of material involved. So if you have water, 1 mole of water, liquid becoming 1 mole of gas, which is what kind of phase change is that? Evaporation, it absorbs 44 kilojoules per mole. But instead of 1 mole, you have 2 moles now. It releases twice the energy. So there are some guidelines that is important when you study these thermochemical equations. Let me read the rules for you. Always specify the physical state of the reactant and products because they help to determine the actual enthalpy changes. Always when you write the thermochemical equation, make sure you write the state, whether it's a solid, liquid, or gas. So here you see methane gas, oxygen gas, water, carbon dioxide, water, gas. But here, water liquid, there is a phase change. There is a different enthalpies. It doesn't matter the water because this is a liquid, this is a gas, there's a phase change. There's an enthalpy change. And then when they multiply, always multiply the delta H. The reversing the equation changes the sign. If methane, oxygen combustion releases energy, combining carbon dioxide and water form methane and oxygen, it absorbs energy. I have a question now. My question is, given the thermochemical equation for photosynthesis is this one. And I have the energy is positive 2803 kilojoules per mole. Calculate the solar energy required to produce 75 grams. So this is the 1 mole of glucose, right? You see in this equation, 1 mole of glucose, you need 2803. But now I don't have 1 mole because I know 1 mole of glucose is 180 grams. How do I know 1 mole of glucose is 180 grams? 1 mole, think about the molar mass. Molar mass of glucose is 180. C6, 12, because 12 is the mass of carbon into 6 plus 1 into 12 plus 16 is the mass of oxygen plus 6. And then I get, okay, it's 180. But now, very first thing is you find the number of moles. Once you find the number of moles, I got 0.416. moles in 75 grams. And then I did, okay, it is the 0.716. So I just multiply these two with 1 mole produce. Okay, I'll do it this way. I'll show you in a minute. Okay. So here at the very first, I find the number of moles, and then which is 70. Sorry. And then I find the number of moles is 0.416 moles, right? 0.416 moles I have. Now if it is 1 mole, I'm getting kilojoules, but I don't have 1 mole now. I have only 0.416 mole. So I mole cancel, and you multiply these two numbers, and I'm getting my answer as 1.17 into 10 to the power 3. So that's how I calculate, okay, this is the energy for this amount of mole. So with that, I think I'm going, okay, I want to escape it. With that, I'm going to stop this question, the part 1, and then I'm coming back to part 2. Okay, I'll come back. I'll meet you in the part 2.